Hello, and thank you for coming to our presentation. My name is Jonathan Beisberg, and I'm a research scientist at the Sonova Audiology Research Center in Canada. And today we will be discussing cortical benefits of DNN-based noise management in experienced hearing aid users measured using FNIRS. To begin, let's discuss listening effort. Listening effort is frequently defined as the cognitive resource allocation needed to understand auditory information, or in other words, the mental energy needed to make out speech. It is an increasingly popular outcome measure because it helps profile one's hearing performance beyond traditional measures like tone and speech audiometry. The problem is, there is much debate over the best ways to measure it. Some attention has been given to neural or brain measures of listening effort, likely due to their objective nature and their ability to index cognitive activity directly from the brain. Research in listening effort during speech and noise tasks has generally implicated heightened activity during more adverse listening conditions in left prefrontal areas in the brain, with recent FNIRS studies also implicating these areas. So what is FNIRS? FNIRS is a relatively new neuroimaging method. It works by emitting infrared light into the scalp. That light then scatters through cortical tissue before some of it is reflected back to detectors on the FNIRS device. Brain activity can then be inferred based on the relative light intensity that is detected. The right image shows a schematic of an 8-channel FNIRS device that goes over the prefrontal cortex. Each channel, or optode, is made up of a pairing of light emitters in yellow with light detectors in purple. A single detector can be paired with multiple optodes. FNIRS can be advantageous over other neuroimaging methods because it can be used in the presence of metal objects, such as hearing aids, unlike fMRI, and has relatively good spatial acuity compared to EEG. It's also relatively affordable compared to these methods. So, how do we apply FNIRS in listening effort research with hearing aids? Well, the first step would be to study whether FNIRS measured oxygenation is sensitive to differences between wearing hearing aids and not wearing hearing aids. And we recently published data on this. In a speech and noise task, unaided listening was associated with heightened oxygenation in the prefrontal cortex compared to aided listening, which we interpreted as heightened cognitive demands in more adverse listening conditions, which was the no hearing aid condition. While the study revealed FNIRS's ability to measure oxygenation between aided and unaided listening, not much else about the findings were exciting, as the benefits of hearing aids have long been documented and established. So the next step for us is to determine if FNIRS would be sensitive to differences between features within a hearing aid, as these findings would inform whether new features in development are associated with real physiological benefits. So in the current study, we are investigating whether FNIRS measured oxygenation would be sensitive to differences between feature on versus feature off processing. And for the feature in question, last summer, Phonak released the Infiniosphere hearing aid, which uses a purpose-built chip implementing a DNN that cleans noisy speech in real time. Early data and feedback suggest that this feature has a very positive benefit for listening and noise, making it a great candidate feature to test FNIRS sensitivity. So the objective of the study was to determine if the sphere feature would be associated with less oxygenation in the left prefrontal cortex compared to a calm and quiet program during a speech and noise task. So for this study, we recruited 26 experienced hearing aid users with an average mild to moderate hearing loss. They were instructed to listen to a sequence of up to 5 sentences in noise and to repeat only the last word, followed by a listening effort rating for all the sentences in the sequence, of course, while wearing the FNIRS device. We used a sentence sequence and not a single sentence to allow for a stimulus of long enough duration to obtain a robust FNIRS measurement. Participants only repeated the last word to avoid the risk of movement during FNIRS recording that might impact the brain response. Participants completed the task in 2 conditions. 1, the calm situation program, which used a combination of omnidirectional microphones and no noise management features, and 2, the sphere program, which used a combination of the DNN and directional microphones. And here is our optode montage. You can see how our optodes mapped onto the prefrontal cortex. We subdivided the cortex into 3 regions, the left lateral, lower medial, and right lateral prefrontal cortices, each subregion comprised of 2 measurement optodes. Now let's look at the behavioral results. If these results went into the expected direction, we could be confident that the experiment was designed as intended. Let's start with the left panel, which illustrates listening effort ratings on the y-axis for the calm situation program on the left and the sphere program on the right. Lower values are indicative of lower rated effort, and we can see that listening using sphere was rated significantly lower compared to calm. On the right panel, we have listening accuracy scores with percent correct on the y-axis. We can see that on average, participants repeated almost 20% more words correctly using sphere versus calm. Together, these behavioral results suggest that sphere was associated with less listening effort and better speech accuracy, validating that this would be a good experimental design to study FNIRS. And without further ado, here are the results. In these plots, we can see the FNIRS results broken down by prefrontal subregions. And here's the time series data of a composite FNIRS value that we call HBDIF relative to the stimulus onset at time 0. The solid lines represent the average response, whereas the shaded regions represent the standard error across all study participants. Red is calm and blue is sphere. And we can see the cortical activity in both the lateral regions on the left and the right panels. However, only in the left region do we see a difference between the programs. We can see that oxygenation is more elevated in calm compared to sphere, suggesting that the brain was more active in the calm condition, which for our study was the more adverse listening condition. And for the purposes of running statistics, we took the average time value between 10 seconds and the end of the time series, which is illustrated on this slide, where we see a simple main effect of oxygenation only in the left lateral region. And this is consistent with our hypothesis that easier listening conditions marked by sphere would be associated with less oxygenation in the brain, reflective of less cortical activity required in order to complete the task. So to conclude, we've provided evidence to suggest that FNIRS as a neuroimaging method can measure differences in cortical oxygenation sensitive to differences between listening using sphere and calm. Less listening effort due to the use of sphere was associated with lower oxygenation in the left lateral prefrontal cortex while listening to speech and noise compared to the calm. We might then speculate that the use of the sphere program may free up cognitive resources for other tasks while listening in noisy environments. So that wraps things up. Thank you for listening, and I look forward to receiving your feedback.